Hi, my name is Bert. As Doug said, I work for NCAR down in Boulder, but since I live here, Kevin has been so gracious as to offer me an office at the Sub-Zero Lab, so that's where I spend most of my days. What I'm going to talk about today, something very different, is climate change and the effect that this will have on avalanches. Because we know that temperatures are changing, precipitation patterns are changing with the changing climate. All of those we know they have an effect on the snow and stratification of snow. So it's only plausible that snow stratification and avalanche activity will also change in the future climate. Now the question is, can we get a feeling for what this change might be? And that's what this project was about, kind of trying to get a grasp of avalanche activity in a warmer climate. Now, to do that, basically we strung together a whole bunch of models, starting with climate models. We have 10 years of past climate simulations and 10 years of future climate simulations at a 2-kilometer resolution over Switzerland. I have to say this whole study was done over Switzerland, but we can talk about how this translates to the US later. So 10 years of past climate, 10 years of future climate under RCP 8.5 scenario, which is a scenario with relatively high degrees of warming, lots of coal use, so lots of emissions, and not a very favorable scenario. From these simulations, we take 70 locations roughly that correspond to weather stations across the Alps, mainly in the Alpine. So that gives us a pretty representative sample of snow conditions there. And the reason we do this is so we can compare the past climate simulations to these observed snow heights and temperatures, just to see if we're doing all right with the simulations, and that gives us more confidence in the future simulations as well. We run those time series for those locations through the snowpack model. Snowpack is a model developed at SLF in Switzerland. It's an energy balance model for the snowpack, so it takes in all the energy inputs, outputs. It's widely used to assist in avalanche forecasting. This model gives us properties of the snowpack, so new snow heights, liquid water content, all that, but it also allows us to simulate the stratification. So we simulate a snow profile for each day of our simulations, and we do not only simulate this profile on a flat surface, but also on a 38-degree incline on all the 4 cardinal directions. So this allows us to see, okay, what's the effect on different aspects. And then the last model that we use is a machine learning model that my friend Steffi developed. This is a model that takes into account the properties of weak layers and slabs, and based on a whole bunch of observed snow profiles and observed Rutschblock data combined with simulated snow profiles, this model basically learns what is stable and what is unstable. And based on that, we can assign these simulated profiles a stability score, whether they're stable or not. So this allows us to see, okay, how many of these profiles are stable, how many of them are unstable. All right, so now I'm going to take you through this modeling chain, more or less, and look at some of the results along the way. So starting off with the climate models, here what we can see is the past climate in the left column, and then the future climate in the center, and the difference. And this is the precipitation for each of the 4 seasons, so winter, spring, summer, and fall. What we see is a clear decrease in precipitation in summer. It's a lot drier, and an increase in precip over the winter. And now, before you all get excited about more snow, the downside, of course, is that this is coupled with a pretty big increase in temperatures. So from roughly 2 to almost 4 degrees of warming is what we're going to see towards the end of the century. So this is, just to make sure it's like the last 10 years of this century. So yeah, around 3 degrees of warming in winter, not ideal. That's 3 degrees Celsius, or which is roughly 5 degrees of Fahrenheit, or freedom units for y'all. So what does that look like? Warmer temperatures, more precip, a lot more rain on snow. So here we have the rain on snow rate, so basically all the hours where there's a snowpack and rain falling. And then what you see is that in the future, in the orange, we see an increase on almost all the months. So even in like high winter, December, January, February, a lot more rain on snow. So not great, except for June and September. That's awesome. So obviously there's no more snow in June and September, right, in the future climate. This is why we're not seeing rain on snow. So if we look at the length of the snow season, we can also plot that for all these simulated points. In a past climate, we see this are the snow season lengths, the number of days with snow on the ground. And then in the future, there's significantly fewer days with snow on the ground. So not ideal. Here again, it's the same plot. This is the absolute change in the number of days. So we're seeing like a 50-day decrease on average. And if you then plot that as a fraction of the snow length for each of those locations, you see, well, up to 40% decrease in snow season length for low elevation stations, especially on south-facing aspects. So not ideal. Mean max snow depth, kind of a similar picture, although I have to say this mean is the mean over the entire hydrological year, so from October to September. So a lot more days with no snow make this mean go down pretty quickly. If you take the mean only over the days where there is snow on the ground, it's not as dramatic, but still there is a pretty big decrease. And then for the max snow height, again, up to 50% decrease on low elevations and a pretty strong elevational gradient. So again, not the best outlook. Don't shoot the messenger. Let's look at avalanches, because that's what we're here for, right? So the first thing we wanted to look at is wet avalanche activity. Now, snowpack doesn't model avalanches per se, but we can use some clever tricks to get an idea of what the wet avalanche activity in the future may look like. So two friends of mine, Nanda and Cesar, they a while ago published something where they showed that once the liquid water content exceeds 6% in the snowpack, this corresponds pretty well to both the temporal onset as well as the layer where wet avalanches tend to break. So we can use that by looking at the first day of the season that 6% of liquid water content is exceeded in our simulated snow profiles. And if we do that, we look at the first day this happens in each season, and we take the mean over the past climate and the mean over the future climate, and we can look at the shift of those days. So what we then see is that on average it's like around 25 days earlier in the season is when we're going to see the first signs of wet snow avalanches happening. And that's relevant for ski resorts, for example, because sooner and sooner will you see that these wet slides start occurring. And for example, last year we had a pretty good year here in Montana, and I remember a lot of people wanted Bridger Bowl to stay open longer. And correct me if I'm wrong, but I understood that one of the concerns to not do that was that they couldn't guarantee safety with regards to wet slides. So that is a concern that probably going to see more and more in a lot of resorts, and more and more on north-facing slopes. They seem to be, so the yellow dots seem to have a slightly stronger decline than the north-facing slopes. All right, let's talk about dry slab avalanches. So I mentioned this machine learning model before. This model, it's trained on data from roughly 700 snow profiles and Roots block observations, and basically a random forest model. So you feed a lot of data, it then tells you a relation, and this helps you to predict the instability. So this looks at the weak layer and the slab above for the whole snowpack, and then assigns the profile a overall stability score. And once the score is above 0.77, this is deemed unstable. So we can use that to look at all of our simulated snow profiles. We simulate one profile per day, so then we can get a score for each day, if it's a stable day or an unstable day. And if we do that, we get plots like these. So for the past climate, for the future climate, on the 4 cardinal aspects. And then what you see is that there's a pretty big decrease in unstable days, which is not really surprising, right? We have a lot shorter snow season. So if there's no snow on the ground, it's really hard for that snow to be unstable. But the question then becomes, is this decrease in instability that we're seeing, is this only because the snow season is shorter, or is there something else going on? Well, we can do that by kind of correcting for the change in snow season length. So we take the share of unstable profiles for each season, and then the plot looks roughly like this. So this is the percentage of unstable profiles in the past climate, and on the right, the future climate. And again, we see a pretty strong decrease still, and especially on north-facing slopes. There, the decrease is bigger than on the other slopes. And this is, once you think about it, or think about the energy balance of the snowpack, this makes sense, right? Because on south-facing slopes, the main energy input to the snowpack is solar irradiation, shortwave radiation. And that doesn't change in a warmer climate. What does change is the air temperature and long wave input. And on a south-facing slope, those are only a small portion of the energy input. Whereas on a north-facing slope, that's all that's going into the snowpack in terms of energy. So on a north-facing slope, relatively, a lot more changes than on a south-facing slope. And that kind of explains why north-facing slopes see this bigger change than the other ones. And then the other thing is that north-facing slopes are more unstable to begin with, so there's more to be gained, so to say. We can plot this as a change signal. So this is absolute change in the number of days, the decrease in number of days, and then the relative change. So this is the change that is due to increasing air temperatures. And then what we see is, again, the strong decrease in north aspects. And so if you're working in a ski resort or securing a highway corridor, this kind of tells you that maybe you need to buy less explosives or hire fewer people in the future. And if you're going out skiing, well, I wouldn't take my word for it, but it looks like it might be slightly 5-10% more stable in a future warmer climate. So what we've seen is, based on simulations of past and future climate, we can kind of, by using all these models, simulating the snow stratigraphy, we can get some insights over the future climate. For one, we're going to see a really big reduction in the number of days with snow on the ground. So the snow season is getting shorter. Max snow heights are going down. And we're going to see more rain on snow. And then in terms of avalanches, wet snow avalanches are going to start earlier in the season. And in terms of dry slab avalanches, we're going to see a big decrease in the number of unstable days. Again, that's mainly due to a shorter snow season, but also in some part due to higher temperatures that we're seeing. So with that, I just want to leave you with this plot. I just got back from Switzerland, and this is a map of the relative snow height in the middle of March. Yeah, and what you see is a pretty big decline in low elevations and average to above average snow heights higher up. And I think this is what we're going to see more and more going into the future. So low elevation snow is kind of going away, or the season's getting extremely short, whereas high up on the mountain we still will have a pretty decent snowpack, but there too the season's getting shorter. Yeah, I wish I had a better news for you guys, but it is the way it is. Again, don't shoot the messenger. Get after it while you can. And yeah, let me know if you have questions.
Pick-me-up presentation. It's going to be more stable!
An optimist, I like him.
Sure you did.
How do you correlate something, if I may ask, how do you correlate something like the experience we had this season with forced snow, warm temperatures, and extended considerable danger?
Well, generally low snow years are generally more unstable, right? Like high snow years tend to be more stable. If you have big snowfall and consistent snowfall, it tends to be.
So it wouldn't be temperature related, it would just basically be driven by snowfall?
I'd say in this case, yes. But it's always hard to, this is the problem in general when you talk about climate change. There's always somebody who says, oh, but you know, it was very cold yesterday, so it's all bullshit. It's like, no, climate and weather are two different things. Like climate is the long-term statistic, weather are singular events. So taking one winter and saying this is due to climate change or whatever, that's really hard. You need to really look at long-term statistics to be able to say anything about that. But yeah, this was a bad winter. Last year I was in Switzerland and it was green. I was literally walking down the hill with my skis at the end of the day. I think there's variability in all continents, and that's going to continue to happen. But as the mean gets lower, then with the same variability, you get into worse and worse years.
With your, when you're looking out and doing these snowpack simulations, I'm wondering, like, how do the snowpack simulations account for maybe more extreme weather patterns?
So
is that built in?
Should be covered in the climate simulation, right? So this is a physical climate model. So this, I actually know that these same simulations, other people have looked at extreme precipitation, and there is indeed an increase in extreme precipitation. So you see more extreme precip events happening. So that automatically feeds into snowpack. Yeah.
Gotcha.
But it'd be interesting to see, like, do we have more storm slabs because of that? Bigger snowfall events might lead to more storm slabs versus persistent weak layers. I mean, there's a lot of data in here that I still need to shift to.
Yeah, I mean, it'd be really interesting to see, well, are we forming, that would suggest that you aren't forming these really bad persistent, like, I've always wondered, well, are we going to get like long periods of dry weather interspersed with long periods of wet weather? Mm-hmm. Because if we get that, then you need to hire more people because it's going to be, the storms are going to be crazier, right? Because
totally.
You're going to have but all that is against this backdrop of losing our snow.
Yeah.
So.
No, for sure.
Yeah.
How did you drive stability from simulated worst block results?
So this model, I should have put in a reference to Steffi's paper, but what they did is basically you have a lot of observed snow pits with observed Woods blocks, and then for the same days they have the weather station data, so they simulate the same snow profile, and then manually they detect the weak layers where the root block failed, and this is how the model learns, okay, this is weak enough to fail on. And you do that over and over again until at some point the model becomes really good at identifying these weak layers. It's kind of the same as a machine learning model where you give it pictures and you say, is this a cat or a dog? And initially you have to tell it, this is a cat, this is a dog, and at some point it knows what is what. So this is sort of how they did that for the stability as well.
Okay.
So really,
We can talk about it.
Yeah, we can definitely talk. I mean, I have more slides, but I don't know how we're doing on time.
Slightly witty question. Why did you use random forest and not different type of forest, like regression boosted forest and stuff like that?
You're going to have to ask Steffi. I
Okay.
have no clue. No, I don't know. Anybody else?
Your climate models, I'm just curious if you even know, were you taking into account like possible outcomes of like changing ocean currents and things like that, or it's just so tied to Gulf Stream?
Yeah.
Did you look at different possible outcomes?
No. So these models, so basically how this works, let's see. Oh, should I go back all the way? I mean, it's kind of a stupid picture, but it's not one model, it's a whole chain. So you start with a global model that incorporates the ocean and everything, and then you use that to force a smaller model, in this case over Europe, and then an even higher resolution model over your target domain. So yeah, to answer your question, yes, it's in there. And it's a whole
one
chain.
outcome of Gulf Stream. Like, there's just not much agreement on ocean currents currently. There's a lot of disagreement as far as I can tell. So I was just curious, like.
Yeah, I see your point. Usually we tackle that with ensembles, so we run a whole bunch of models. For this study, I picked one because it's just too much work to do them all. But yeah.
Maybe more so like the stability inference, like they're all the same.
Sorry, I'm really deaf. So
Like the inference about stability seems like it could be variable, but could it be like more applicable, maybe say less large avalanches happening? Is it less so?
Yeah, that's I'm hesitant to go that far. Would be interesting to. I actually had a discussion with somebody about this, if we can simulate this for the future and look at it, and I think we could, but not based on these data. So I'd have to dig a bit deeper. I'm hesitant to say we're going to have bigger or smaller avalanches. That's too much.
it's going to be more stable.
Thanks a lot, Bert.
Thank you. Thanks.